All right, everyone, we are in our two-dimensional kinematics notes, and we're going to be solving example number 1. Now, before we do so, I want to remind you a couple things that we need to remember about kinematics, and specifically the kinematics equations. You do need to remember here that the kinematics equations have been solved for constant acceleration. So that basically means that if the acceleration changes or if it's different, you have to use different equations. You have to split it up, and we've looked at problems like that. Second thing to remember here is that because the kinematics equations are one-dimensional, you need to split your motion up into x direction motion, and you have to split it up into y direction motion. So that's basically what we're going to do here. As long as we keep track of these two dimensions at one time, we are in good shape. All right, so let's go down to our example. All right, so here it is. This is example 1. This is what we'll be looking at. And we have an airplane. It's flying horizontally. It's got a certain speed, and it's at a certain altitude of 1.5 kilometers. And a wheel falls off. So this is a terrible occurrence. Wheels on planes are extremely heavy, so you wouldn't certainly want to be underneath this thing. But we want to know, first of all, what horizontal distance does this wheel travel before striking the ground? And second of all, what is the wheel's velocity when it strikes the ground? All right, so what you're going to have you do here is stop the video at this point. I'd like you to draw the picture that would represent this situation so that we can actually go ahead and solve it. Pick up with me once you've done your picture. All right, so here's at least part of the picture that we're looking at. We know that, again, this plane's flying horizontally. We know that it is moving in a horizontal direction, as I just said. And something else to keep in mind here is because the plane is traveling at a 500 kilometers per hour speed, the wheel, as it falls off the plane, is also going to be traveling at 500 kilometers per hour. That's Newton's first law, the law of inertia. Things in motion tend to stay in motion. Things at rest tend to stay at rest. So our wheel, which is in motion with the plane, continues in this state of motion at the same rate at speed that it had before. Well, we're also ignoring air resistance in all these. I guess I forgot to mention that, but that's kind of one of those things we assume, at least for now. We'll look a little bit later, especially when we deal with energy. What happens when we have air resistance? What happens when there's friction? But for now, let's not worry about that. Next thing we're told is that we were at an altitude of 1.5 kilometers. I've taken the liberty to convert this to meters. Generally, we want to get to the MKS system, meters, kilograms, and seconds. So I've taken that conversion, and I've already done that here. Now, often people want to draw the delta y from the ground level up. But what you got to remember here is our displacement is always labeled from the point it starts and points in the direction to where it ends up. So since the wheel starts here and it ends down here on the ground, our displacement has to be from the top to the bottom. So you want to be careful here. This is one of those common mistakes people make. Likewise, the displacement in the x direction, which is actually one of the things we want to look for, is from the position where it's released from the plane, or it falls off the plane, and it ends up pointing to the place where the wheel actually strikes the ground. Now, I've purposely covered up the velocity here. I want you to really think hard about this, specifically thinking about what acceleration is going to be occurring, and get an idea of what the velocity at the ground level is going to look like. All right, and I'm going to pause it for just a moment and then come back to you in just a second. All right, so here we are back with the final velocity. And again, a couple of things to remember here is a lot of people want to simplify this and say, oh, well, it hits the ground, it's got to be stopping. Well, while that's true, you're dealing with two different forces then. You're dealing with the force of gravity pulling it down, but then you're also going to be dealing with a force of the ground pushing up on it. And again, our kinematics equations don't work for this. So we are looking at that instant as this is coming flying down here, and it's at that instant just as it's striking the ground. So it ends up being the instantaneous velocity at the instant, hence the word instantaneous, at the instant that it strikes the ground. Okay, so it hasn't actually hit the ground yet. It's just that split second before. So as we're having this wheel fall off, we know that it is going down and it's under the influence of gravity, which of course we know is 9.8 meters per second squared. That's the only force that we're dealing with in this problem. Of course, it's a constant acceleration, so again, the kinematics equations work here well. And we know that there's no force to the left or to the right because there's no air resistance. So there is no acceleration here in the x direction. So that's why our x velocity remains constant. But we, of course, also gain some amount of, we're going to gain some amount of y velocity, and that's the reason we have this downwards arrow drawn here. So put these two together and you end up with the resultant vector that looks like this. So ultimately this is the resultant vector we're going to be looking for. As you can see here in the knowns, what I like to do here is separate these knowns into two sections, and I have the x direction knowns and I have the y direction knowns. So I've done this because again you don't want to put your x direction knowns with your y direction knowns in the equations. Remember, these are one-dimensional equations, or at least the way we're using them. So you need to keep track of the x's separate from the y's. All right, with that being said, I'd like you to now come up with a strategy on how you might go about solving this, and stop with me here and pick some equations and some strategies on how you might actually go ahead and solve this. All right, so here we are. We're going to try to figure this out. We wanted to find this delta x, in other words, how far it's traveled in the x direction. So one of the first equations I look at here is our equation. Whoops, I just lost it. Let me go back and pull this up. All right, we got it back. So again, I do want to find this delta x. So one of the first equations I go to is my speed equals distance over time. And right away, I hope you can see here that delta x and distance in this case are going to be kind of similar quantities, but I can't use this because, of course, I'm missing the time. Likewise, in this equation, there's delta x. I know my average velocity is going to be this 500 kilometers per hour, but again, I can't do this because there's two things in here that are unknown, that both the delta x and the delta t are unknown. This one, not a good candidate, doesn't even have delta x in it. Likewise here, same thing. In fact, this equation right here really is derived from this equation, as we've seen. Down here's another good example of delta x. We need, but here we go, again, need time, so let's throw that one out. Here, this is a promising one. We have a delta x in there. We have an acceleration of 0 meters per second, and we have both the final and original velocities of 500 kilometers per hour. Now, I'll let you play around with this one, but I will tell you this one's not going to work either because these two things are equal, and this is 0, so it actually cancels out the delta x. So even this one doesn't work. Over here, once again, we're stuck with this time problem. So what this really comes down to is that we need to find the time first. And so what we're going to do here is figure out a way to find the time it takes for this wheel to fall from here down to here. The only way we can figure that out is if we use the y direction to do so. So I'm going to pull up my other picture, and we're going to take a look at this. This is the equation part of it here. And again, we are going to find the time first. Once we find the time, that's going to allow us to find the delta x. That was kind of the issue here, is that without knowing the time, we can't actually do anything to find the delta x. So let me slide this over. To find the time, I actually ended up using the y direction. Since it's moving horizontally, our original velocity in the y direction is 0. We know our delta y, so that's something we know. Our a happens just to be the 9.8 meters per second squared. And then, of course, we can solve for t. So again, I'm doing some algebra here, isolating the t to get it by itself, and I've done so right here. Moving on, I'm going to try to put this in, and I move back over to the x direction and say, all right, well, I know this t, or I have a number for it. I can then plug this back in, knowing the acceleration in the x direction. Again, notice this is the x direction. Here, the x direction has no acceleration, and again, that's because there's no force that caused it to accelerate. So I end up, that term here cancels out, the 1/2 at squared term. So I'm basically left with the delta x equals the original velocity, again in the x direction, times the time I found in the y direction. Again, since time is not a vector, direction doesn't really matter for that. So let's see what happens here. Looks like I've solved both here. I end up with, after putting the numbers in for the time, I end up with 17, well, you can read it there, it's 17.496 seconds. And then over here, I put this in. Now you notice, I'm noticing here that I probably want to make a conversion so that I can get this into units that are in the MKS system. So I end up actually doing that. Please notice here that this kilometers per hour does not agree with this. Now I could convert this seconds into hours and this would work, and then I'd have a units, of course, in the kilometers, but I chose to convert my kilometers per hour into the meters per second, again the MKS system. So once that's said and done, looks like I get 2,430 meters for our delta x, which our delta x, let me bring that back up here, our delta x is this. So it looks like it's traveling just over, or just under 2.5 kilometers actually. All right, let's see what you would do to find part B. I'd like you to go ahead and stop, think about that for a moment, and pick up with me once you think you know what to do. All right, so here we are back at part B, and if we want to find the final velocity, in other words, the velocity with which this ball, or I keep saying ball, but it's at the wheel, strikes the ground, we're going to use the x direction, or sorry, the y direction. And since we just found the time, and we know the acceleration, and we know that this is traveling horizontally, so there is no zero velocity in the y direction, this is a good candidate for finding the final velocity. So after plugging my numbers in, and again, these are y direction numbers, I end up with 171 meters per second. Now a lot of people would say, well, I'm done here, but I want to refresh our memory back here in the picture to start. What we just found was this component of this vector here. And so this 171 meters per second does not actually represent, again, let me repeat, it does not represent the final velocity. The final velocity is actually this vector right here. So ultimately, what this means is that we need both the y component and the x component of the final velocity to actually do the actual, to find the overall velocity. So of course, based on our picture, we know that these two vectors are at right angles to one another. It's the reason we chose the x and y direction in the first place, because they're at 90 degrees. We also know that they add together like vectors, and so we can use Pythagorean theorem here to actually find the magnitude of the vector. Once we find the magnitude of this vector, we can then actually go and use a little bit of our trig identities to actually go through and find this angle. And so I've done that here. And again, we should be pretty familiar with those trig identities. And so in the end, what do we end up with? Well, we end up with a velocity which has a magnitude of 220 meters per second, and it's at an angle of 50.9 degrees below the horizon.